Time and space are not what they seem. They weave together into a single fabric called space-time, the very stage upon which our universe plays out. Think of it as a cosmic trampoline, stretched taut, but bending and warping under the weight of planets and stars. By the end of this journey, you will see reality in a completely new way. We will explore how black holes tear at this fabric, and how you could theoretically travel to the future just by moving fast. What single idea about the cosmos makes you question everything you think you know? This single idea of a unified space-time comes directly from Albert Einstein's revolutionary theory of relativity. He proposed that space and time are not independent stages, but are woven together into a single four-dimensional fabric. Think of it like a trampoline mat, a single continuous sheet. Now, place a heavy bowling ball in the center. The mat stretches and curves downward under its weight. That is exactly how mass and energy behave in our universe, warping the very fabric of space-time around them. This curvature is not just a bend in space, but a bend in time as well. What we feel as the force of gravity is simply us following the contours of this warped stage. Every single event in the cosmos, from a supernova explosion to you drinking your morning coffee, happens at a unique address within this four-dimensional grid, a specific point in both space and time. This profound connection means that if something massive enough moves, it can send ripples across this cosmic fabric, like jiggling the trampoline and creating waves. We now call these gravitational waves, and we can actually detect them. This challenges everything about our daily lives, where space feels static and time flows forward on its own. But they are one inseparable entity, the first astonishing fact that reshapes our entire reality. Einstein's insight completely redefined gravity itself. It is not a mysterious force reaching across space to pull objects together, as Isaac Newton envisioned. Instead, gravity is the result of the curvature that mass and energy create in the fabric of space-time. Picture that trampoline mat again. A heavy sun warps the mat, creating a deep, smooth depression. Now, roll a smaller marble representing Earth across this curved surface. The marble does not need any invisible strings pulling it. It simply follows the natural curve created by the sun's weight, tracing an orbit around that central depression. This elegant motion is not due to a force, but to the shape of the stage itself. Our entire solar system operates on this principle, with every planet and moon following the invisible grooves carved into space-time by the sun's immense mass. What you feel as your own weight is not really a force pulling you down. You are being pressed against the curved space-time created by our planet. The ground pushes up, preventing you from following the natural path down the slope of the warped geometry beneath your feet. This radical idea was put to the test in a famous experiment during a total solar eclipse in 1919. If the sun really warps the space around it, then light from distant stars should bend as it passes near the sun, just as a marble's path would bend rolling across a curved surface. During the eclipse, when the moon blocked the sun's blinding light, astronomers measured the positions of those background stars. The starlight was indeed deflected, exactly as Einstein's theory predicted. This was the first direct proof that space itself is malleable, bending around massive objects and guiding everything within it, from the planets to the very light we see. This warping of space-time does far more than just bend the paths of planets and light. It directly warps time itself. Time dilation is a real and measurable phenomenon, a stunning consequence of the flexible nature of space-time, where time passes at different rates depending on your speed and the local strength of gravity. This is not science fiction. In 1971, physicists Joseph Haefel and Richard Keating took several incredibly precise atomic clocks, synchronized them with a clock at the United States Naval Observatory, and then flew some of them around the world on commercial airliners. Upon their return, they compared the traveling clocks to the one that had stayed firmly on the ground. The clocks that had been in motion were measurably behind, by mere billionths of a second, but they were undeniably behind. Time itself had passed more slowly for the clocks in motion, just as Einstein's equations had predicted. This effect is not just a laboratory curiosity. It is a daily reality for the global positioning system. Each GPS satellite orbits high above Earth, moving at thousands of miles per hour and experiencing a weaker gravitational pull. Both of these factors cause time on the satellite to run faster than it does for us on the surface. If the satellite's clocks were not constantly corrected for this time dilation, the entire system would become useless, accumulating errors of several miles within a single day. Your phone's map application works only because engineers have hardwired Einstein's theory of relativity into the system. This means that every astronaut who lives aboard the International Space Station is, in a very real sense, a time traveler to the future. Orbiting at high speed in Earth's weakened gravity field, their clocks tick just slightly slower. Over a 6-month mission, an astronaut ages about 0.005 seconds less than those of us on the ground. The difference is tiny, but it is definitive proof that the flow of time is not a universal constant. It is a personal experience shaped by your journey through the cosmos. By moving fast enough, or by spending time near an immensely powerful gravitational field, you could, in principle, leap years or even millennia into the future. This is our third astonishing fact, that the universe has built-in mechanisms for time travel, and we are using them every time we check our location on a map. But if warping space-time can slow a clock, what happens when the warping becomes absolute? Black holes are the ultimate expression of gravity, places where the fabric of space-time is not merely bent, but torn. At their heart lies a singularity, a point of infinite density where the curvature of space-time becomes infinite, and our known laws of physics simply cease to apply. The sheer mass of a collapsed star is compressed into an immeasurably small point, creating a gravitational pull so fierce that nothing, not even light itself, can achieve escape velocity. The boundary marking this point of no return is called the event horizon. Crossing this invisible threshold is a one-way trip. From our perspective outside, any object falling in would appear to slow down, freezing in time as it approaches the horizon, its light stretching into an infinite red shift until it fades from view entirely. For the outside universe, time at the event horizon effectively stops. Yet, for the unfortunate traveler crossing that line, the journey continues relentlessly inward. Once inside, the roles of space and time are thought to swap. Your direction toward the singularity is no longer a choice in space. It becomes an inevitable future, as unavoidable as tomorrow becoming today. The gravitational forces would pull more strongly on your feet than your head, stretching you into a long, thin strand of atoms in a process physicists call spaghettification. These are not just theoretical ideas anymore. In 2019, the Event Horizon Telescope collaboration unveiled the first ever image of a black hole, a fiery ring of light circling the dark shadow of the event horizon at the heart of the galaxy M87. That iconic image, a blurry orange donut of light, was our first direct visual evidence of the monster's silhouette, a profound confirmation that these cosmic paradoxes are undeniably real. They are the most extreme laboratories of the universe, where space and time lose all familiar meaning, presenting us with the fourth astonishing fact about our reality. That iconic image of a black hole shows space-time torn apart, but on the largest scale, the fabric of the cosmos is being stretched. In the 1920s, astronomer Edwin Hubble made a staggering discovery that redefined our cosmic context. By observing distant galaxies, he found that nearly all of them are moving away from us, and the farther away a galaxy is, the faster it appears to be receding. This was not because galaxies are racing through a static space. Instead, the space between them is itself expanding, carrying the galaxies along for the ride. A simple analogy is a loaf of raisin bread rising in the oven. As the dough expands, every raisin moves away from every other raisin. From the perspective of any single raisin, all the others are retreating, with the most distant ones appearing to move the fastest. The universe is not expanding into some empty void beyond. There is no outside. It is the very grid of space-time, the fabric of reality itself, that is stretching, increasing the distance between all points that are not gravitationally bound. This realization points directly back to a cosmic beginning, a moment of immense density and temperature we call the Big Bang. The most profound evidence for this is the cosmic microwave background radiation, a faint afterglow of heat that permeates all of space. This is the cooled and stretched remnant of the universe's first light, a snapshot from when the cosmos was just 380,000 years old, and it provides a baby picture of the universe, glowing with the evidence of its explosive origin. Yet, the story grew even stranger. In the late 1990s, astronomers discovered that this expansion is not slowing down due to gravity, as everyone expected. It is speeding up. Some mysterious repulsive force, dubbed dark energy, appears to be stretching the fabric of space-time at an ever-increasing rate. We do not know what dark energy is. It constitutes about 68% of the universe and is one of the greatest unsolved puzzles in all of science. This means the cosmic stage is not just stretching, it is accelerating its own growth, pulling the distant galaxies away from us so fast that their light will one day fade from view entirely, leaving a future sky far emptier than the one we see today. If the fabric of space-time can be stretched and warped, could it also be punctured, creating a cosmic shortcut? Wormholes, formerly known as Einstein-Rosen bridges, are exactly that, theoretical tunnels through the folded geometry of the universe. They emerge as valid, though highly speculative, solutions to Einstein's own equations of general relativity. Think of space-time as a vast sheet of paper. The normal journey from one edge to the other is a long, straight line across its surface. But if you fold the paper so that two distant points touch, you can poke a hole directly through the newly connected layers. A wormhole would be that tunnel, a bridge connecting two otherwise unimaginably remote locations, potentially allowing for travel that would bypass the cosmic speed limit of light itself. The mathematics suggests these bridges could even connect to entirely different universes, but here is the catch. These theoretical passages are notoriously unstable. According to our current understanding, the tunnel would collapse into a singularity faster than even a single photon could traverse it. To keep a wormhole open and navigable, you would need a form of matter with truly bizarre properties, something known as exotic matter. This is not just rare or unknown material. It is matter that theoretically possesses negative energy density, effectively pushing the walls of the wormhole apart and preventing its catastrophic implosion. While such matter is not forbidden by physics, we have never observed it in nature, and its existence remains one of the biggest hurdles to making wormholes more than just a beautiful equation. This has not stopped them from becoming a staple of science fiction. From the shortcut in A Wrinkle in Time to the navigable tunnels in Interstellar, capturing our collective imagination about the possibilities of interstellar travel. The thrilling question for scientists today is whether some form of stable wormhole could exist without requiring impossible amounts of this exotic material. Could quantum effects on a microscopic scale provide the necessary stabilizing force? The research continues, probing the deepest layers of theoretical physics. For now, wormholes stand as one of the most tantalizing what-ifs in all of cosmology, a ghost in the machinery of Einstein's universe, reminding us that the fabric of reality might hold secrets even more astonishing than we have yet dared to dream. The same cosmic fabric that can be stretched into a vast expansion or torn into a black hole can also ripple like the surface of a pond. For a century, Einstein's theory predicted these gravitational waves, but they were thought to be so faint we might never detect them. Then, on September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, made a discovery that shook the scientific world. Its twin detectors, separated by 1,900 miles, recorded a nearly imperceptible shudder in reality. The signal perfectly matched the final moments of two massive black holes, each about 30 times the mass of our Sun, as they spiraled into each other and merged in a cataclysm over 1 billion light-years away. This was not an observation made with light or radio waves. It was a direct measurement of space-time itself ringing like a bell. Gravitational waves are literal ripples in the fabric of the cosmos, generated whenever massive objects accelerate with extreme violence. Imagine the aftermath of a stone dropped into a still pond. The ripples spread outward, alternately stretching and compressing the water's surface as they travel. A gravitational wave does the same thing to space itself. As it passes through you, it would minutely stretch your body in one direction while simultaneously squeezing it in the perpendicular direction, then reverse the process. The effect is unbelievably tiny. The wave detected by LIGO changed the 4-kilometer-long arms of its detector by only 1,000th of the diameter of a proton. To measure such an infinitesimal change, LIGO uses laser beams traveling down perpendicular vacuum tubes. The lasers bounce off mirrors and recombine. A passing gravitational wave alters the length of one arm relative to the other by that minuscule amount, causing the laser light waves to shift out of sync and creating a detectable interference pattern. It is the most precise measuring device ever built, listening for the faintest whispers of the universe's most violent events. This new sense gives us a completely different way to perceive the cosmos. Light can be blocked, absorbed, or scattered by dust. Gravitational waves, born from the pure geometry of space-time, pass through matter almost completely unimpeded. They carry information that is invisible to traditional telescopes. With them, we can directly probe the properties of black holes, objects that emit no light by their very nature. The pitch and amplitude of the waves tell us the masses of the colliding objects and the ferocious speed of their final orbits. We can even test if the resulting object is indeed a black hole by listening to the ring down, the final vibrations as the new, larger black hole settles into a stable shape. This is like hearing the shape of a bell in the sound it makes. Every collision we detect adds a new data point, a new sound in a growing cosmic symphony that reveals the dark, violent side of the universe we could never before see. We are no longer just stargazers. We have become listeners, hearing the very space-time we inhabit vibrate with the echoes of creation. Listening to the echoes of colliding black holes, we are probing the very edges of our knowledge, but the ultimate question remains. Where did the stage itself come from? Our eighth astonishing fact confronts this directly, suggesting time itself may have had a definitive beginning. A moment of creation we call the Big Bang approximately 13.8 billion years ago. This is not merely the start of matter and energy exploding into a pre-existing void. It marks the origin of space and time as we understand them. The concept of a beginning to everything is difficult enough, but the true challenge lies in what came before. According to our best models, there was no before. Asking what happened before the Big Bang is like asking what is north of the North Pole. The question itself loses all meaning because time, the very framework for cause and effect, did not exist. Our intuition, built on a lifetime of sequential events, rebels against this idea. We are wired to think of every effect having a cause, every today following a yesterday. Yet, if time began with that initial event, then the chain of causality itself has a starting point. The universe could have simply popped into existence from nothing, because without time, there is no prior state to consider. This is where our current laws of physics, including Einstein's magnificent general relativity, reach their absolute limit. The equations describe a universe that is incredibly dense and hot as we rewind the cosmic clock. But at the precise moment of the Big Bang, the density and temperature become infinite. This is a singularity, a point where the mathematics breaks down completely, and our understanding fails. It is not that the universe was an infinitely small point within a larger space. Space itself was contracted to a point. To peer into that first fleeting instant, we need a new set of rules, a theory that can marry the vast cosmic scales of general relativity with the bizarre, probabilistic world of the ultra-small, described by quantum mechanics. This sought-after theory of quantum gravity would describe the universe when it was smaller than an atom, a realm where the fabric of space-time may not have been smooth and continuous, but a chaotic, foaming sea of potential. In some of these speculative models, time as a fundamental concept might dissolve away entirely, replaced by more primitive relationships. Perhaps our arrow of time is an emergent property, a large-scale illusion born from the increasing disorder of the universe, much like a movie that only makes sense when played forward. The profound mystery is whether time truly had a single starting gun, or if our cosmic beginning was merely a transition from a prior state of existence we cannot yet comprehend. Yet even the violent emptiness of a black hole is not truly empty. The very fabric of space-time, down at the smallest conceivable scales, is a seething, bubbling cauldron of activity. This is our ninth astonishing fact, that what we perceive as a perfect vacuum is anything but. According to quantum field theory, the universe's most fundamental ingredients are not particles, but fields, invisible entities that stretch across all of space and time. An electron is just a localized excitation in the electron field, like a wave rising from the surface of the ocean. Even in a region completely devoid of what we call matter, these fields are never still. They constantly jitter and fluctuate. This leads to one of the strangest predictions in all of physics, the existence of virtual particles. Pairs of particles and their antimatter counterparts can spontaneously blink into existence, borrowing energy from the vacuum for an immeasurably brief moment, mandated by the Heisenberg uncertainty principle. This principle tells us that on tiny scales, there is a fundamental trade-off. We cannot precisely know both the energy of a system and the exact time that energy exists. This tiny loophole in reality allows the void to briefly come alive. A particle and antiparticle pair, like an electron and a positron, can simply appear out of nothing, existing just long enough to satisfy the uncertainty principle before they violently annihilate each other and return their borrowed energy to the vacuum. This endless, frantic dance of creation and destruction is happening everywhere all the time in the space around you, even in the space between your eyes and this screen. It means the vacuum of space has a fundamental energy, a restless sea of potential from which everything emerges. This quantum frenzy has a stunning consequence, one that connects the tiny quantum world to the immense gravity of black holes. Imagine this particle pair fluctuation happening right at the edge of a black hole's event horizon. In the split second the two virtual particles exist, one of them might randomly fall across the point of no return, while its partner is left stranded outside. The trapped particle carries negative energy into the black hole, effectively reducing its mass, while the free particle, now real and unable to annihilate, radiates away into space. This is Hawking radiation. From a distance, it looks as though the black hole itself is glowing, emitting a faint heat. Over unimaginable eons, this slow, steady evaporation means that even the most colossal black holes will eventually shrink, and in a final burst of radiation, vanish from existence. The void itself is not passive. It is a dynamic participant in the cosmos, and its hidden activity may one day spell the end for the universe's most terrifying objects. That quantum sea of virtual particles reveals a universe in constant flux, yet even chaos has its rules. A single, unwavering constant governs the cosmos, the ultimate speed limit of reality itself. Nothing can travel faster than light in a vacuum. This is not a limitation of our engineering, but a fundamental property woven into the very fabric of space-time. The speed of light, approximately 186,000 miles per second, is the universe's absolute speed limit. Think of it this way: space and time are two sides of the same coin, and the speed of light is the fixed exchange rate between them. This constant speed is the same for every observer, no matter how fast they are moving. If you were in a spaceship traveling at half the speed of light, and you turned on your headlights, the light from those beams would still race away from you at the full 186,000 miles per second. It defies our everyday intuition about adding speeds, but it is an unbreakable rule of the cosmos. This rule is enforced by a dramatic consequence. As any object with mass accelerates, its energy and mass begin to increase. At everyday speeds, this effect is negligible. But as you approach the speed of light, the energy required to push you just a little bit faster skyrockets. To actually reach the speed of light, an object with mass would require an infinite amount of energy, a clear impossibility. The object's mass would effectively become infinite as well. This is nature's ultimate traffic law, ensuring that nothing with mass can ever hit that ultimate velocity. This speed limit is not just about travel, it is about the flow of information and causality. Light speed defines the boundaries of cause and effect. Imagine if you could send a message faster than light. You could theoretically send a signal that arrives at its destination before you even sent it. This could create a universe-shattering paradox. You could, for instance, send a message to your past self telling them not to send the message. If you never send the message, how did your past self receive the warning? Breaking the light barrier would tear the logical sequence of the universe apart, allowing effect to precede cause. Our experience of a stable, predictable reality, where causes always come before their effects, depends entirely on this cosmic speed limit. It is the thread that keeps the tapestry of cause and effect from unraveling. This cosmic speed limit ensures a stable flow of cause and effect, yet gravity can warp that very flow right here on Earth. Mass does not just bend the paths of planets, it directly warps the passage of time itself. This phenomenon, known as gravitational time dilation, means that time runs slower the closer you are to a massive object. The stronger the gravitational field, the more time drags its feet. Imagine two identical, incredibly precise atomic clocks. If you place one at sea level and carry the other to the top of a tall mountain, the clock at the higher altitude, experiencing slightly weaker gravity, will tick measurably faster. Over a year, the mountaintop clock would be a tiny fraction of a second ahead of its sea-level twin. This is not a thought experiment. Scientists have confirmed this with astonishing accuracy, proving that the force that holds you to the ground also gently presses on the hands of time, slowing them down. This subtle effect has a very practical consequence that you likely use every single day. The global positioning system relies on a constellation of satellites orbiting high above Earth, where our planet's gravitational grip is weaker. Because of this, the atomic clocks on these satellites naturally run faster than identical clocks on the ground. If engineers did not constantly correct for this relativistic time warp, the GPS signals would become useless within minutes, throwing your navigation off by several miles. Einstein's theory is literally hardwired into the technology in your pocket, but the implications get even more personal. The gravitational field at your feet is ever so slightly stronger than the field at your head, because your feet are closer to the center of the Earth. This means time actually passes a tiny bit faster for your head than it does for your feet. Over the course of your entire life, your brain will be older than your feet by a minuscule, almost imperceptible fraction of a second. You are, in a very real sense, living your life slightly out of sync with yourself. This gravitational time warp is not confined to extreme locations like black holes. It is a fundamental part of your everyday reality, a silent, invisible curvature of time woven into the fabric of your own existence. General relativity paints a beautiful picture of smooth, curving space-time, a seamless fabric that stretches across the cosmos. But what if that fabric, when examined under a microscope of unimaginable power, was not smooth at all? What if it was pixelated? This is our 12th astonishing fact. The radical notion that space and time themselves might be granular at the smallest possible scales. The smooth continuum we take for granted could be an illusion, a kind of cosmic resolution limit. At a scale so minute it is almost beyond comprehension, the universe might be built from tiny, indivisible units of space and time, a fundamental graininess to reality itself. This idea emerges from the desperate struggle to unite Einstein's theory of gravity with the bizarre rules of quantum mechanics. General relativity describes the universe on a grand, smooth stage, while quantum mechanics governs a chaotic, probabilistic world of particles. The two theories are brilliant, yet they are fundamentally incompatible. A major hurdle is that in quantum mechanics, everything is quantized, meaning it comes in discrete, indivisible packets, like the photons that make up light. It seems logical, then, that the stage itself, space-time, might also be quantized. The scale at which this graininess is thought to appear is the Planck length, a distance so small that it is to an atom what an atom is to the entire solar system. At this level, the fabric of space-time may not be a calm, flowing river, but a churning, foaming sea of quantum potential, constantly fluctuating. If this is true, how could we ever hope to see evidence of such an infinitesimal structure? One promising method involves looking at the most violent and distant events in the universe, gamma-ray bursts. These are colossal explosions that send photons racing across billions of light years. If space-time is smooth, all these photons, regardless of their energy, should travel at exactly the same speed and arrive at our telescopes simultaneously. But if space is granular, like a bumpy road, higher energy photons might interact with the foaminess of space-time very slightly differently than lower energy photons. Over an immense cosmic journey, this tiny effect could accumulate. The highest energy photons could arrive a fraction of a second later than their lower energy counterparts, creating a subtle blurring or delay in the signal. Scientists are actively analyzing light from these distant bursts, searching for this telltale signature of a pixelated cosmos. Finding it would force us to redraw our most basic picture of reality, suggesting that the universe itself is composed of a finite number of fundamental building blocks, a digital projection on the grandest screen imaginable. That fundamental graininess of space-time is a deep mystery, but there is a far more personal puzzle we all experience every single moment. Time has a distinct and relentless direction. We remember the past, but not the future. We grow older, never younger. A cup shatters on the floor, but the pieces never spontaneously reassemble themselves. This one-way street of existence is known as the arrow of time, and its origin is one of the most profound questions in all of physics. The strange part is that the fundamental laws of physics, from gravity to electromagnetism, do not actually care about this direction. They are almost perfectly time-symmetric. If you were to watch a film of two planets orbiting each other, or two electrons repelling, you would not be able to tell if the film was being played forward or backward. The motions would look equally natural in either direction. So why does our macroscopic world have such a powerful, irreversible forward march? The answer appears to lie not in the laws of motion themselves, but in a statistical concept called entropy. Entropy is a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time, or at best remains constant. It is the universe's way of saying that things tend to move from states of order to states of disorder. Think of a brand new deck of cards, fresh from the box, with all the suits in perfect sequence. This is a state of very low entropy, highly ordered and statistically unlikely. Now, shuffle that deck just once. The cards become disordered, mixed into a much more random, higher entropy state. You would never expect a random shuffle to return the deck to its pristine, ordered sequence. This relentless increase in disorder is the engine behind time's arrow. The reason we see broken cups, but never self-assembling cups, is simply because there are countless more ways for the cup to be broken than for it to be perfectly whole. The universe is statistically biased toward messiness. The ultimate source of this bias traces back to the very beginning. For reasons we still do not fully understand, the Big Bang created the universe in a state of astonishingly low entropy, an incredibly ordered and dense configuration. Everything since has been the cosmos unwinding, evolving toward a state of maximum disorder and equilibrium. This initial low entropy state is the wound-up spring that has been driving the arrow of time for 13.8 billion years. It is responsible for everything we associate with the flow of time. It allows for the formation of complex structures like stars and planets. It powers the chemical reactions in our cells that we call life, and it gives us the ability to form memories. Our brains rely on irreversible chemical processes to record information, and we can only remember the past because it is a state of lower entropy than the present. Without this cosmic tendency toward disorder, cause and effect would blur, and reality as we know it would cease to exist. This leads to a truly mind-bending cosmic question. If the universe's expansion were to someday reverse in a big crunch, collapsing back into a singularity, would the arrow of time also reverse? Would inhabitants of that contracting universe see shards of glass leaping up to form cups? And would they remember the future instead of the past? Some physicists speculate that entropy might continue to increase even during a collapse, meaning time would still flow forward from their perspective. Others suggest the flow could genuinely invert. We may never know for certain, but the mystery forces us to confront a stunning possibility. The relentless forward march of time, the very foundation of our conscious experience, may be nothing more than a cosmic accident, a fleeting consequence of how our particular universe began. Even the gentle spin of our own planet is subtly twisting the void around it. This phenomenon is called frame dragging, and it is a stunning prediction of general relativity. A massive rotating object does not just warp the space-time around it. It actively pulls that fabric along for the ride, as if space itself were a viscous fluid swirling around the spinning mass. Imagine slowly turning a ball in a jar of thick honey. The honey closest to the ball would stick to its surface and be dragged around in a circular motion. In much the same way, the Earth's rotation is continuously tugging at the fabric of space-time, causing the very grid of reality to twist imperceptibly around us. To prove this was actually happening required one of the most precise experiments ever conducted. The Gravity Probe B mission, launched in 2004, was designed to measure this exact effect. It carried 4 of the most perfect gyroscopes ever built, spheres so spherical they were considered the roundest human-made objects in existence. The spacecraft pointed these gyroscopes at a distant star as a fixed reference point. If Einstein was right, the frame dragging caused by Earth's rotation would very slowly cause the gyroscope's spin axis to drift over time. After more than a year of painstaking data collection, the team announced a triumphant result. They had detected the drift. The minuscule shift was exactly as predicted, a direct confirmation that our planet is not a passive object in space, but an active participant, dragging the cosmic stage itself along with its spin. While the effect around Earth is incredibly subtle, it becomes a dominant and violent force around the universe's most powerful rotators, like Care black holes. These spinning black holes drag space-time around them so ferociously that they create a region just outside their event horizon called the ergosphere. Within this flattened, whirling zone of distorted space, nothing can stand still. The fabric of space-time itself is being swept along at such a velocity that any object caught there is forced to move, corralled into orbiting the black hole. It is a place where the very concept of staying in one place loses all meaning. A cosmic maelstrom where the universe insists you must move with the flow. This frame-dragging effect even offers a potential mechanism for the most energetic explosions in the cosmos. Matter falling into the ergosphere of a rapidly spinning black hole could be whipped around and flung outward with tremendous force, possibly powering the intense jets of energy we see in quasars and gamma-ray bursts. The gentle twist of our own world is a quiet echo of these cosmic storms, a reminder that rotation is not just motion through space, but a profound sculpting of space-time itself. That twisting of space-time by massive objects shapes not just local regions, but the entire cosmos. The ultimate fate of everything, whether the universe expands forever into a cold, dark emptiness or eventually collapses back in a fiery reversal, is written into the very shape of space-time itself. This geometry is not a flat, featureless stage. On the grandest scales, space-time can curve in one of three possible ways, each dictating a different destiny. First, a flat universe. This is the most straightforward geometry, where the rules of Euclidean geometry we learned in school apply. Parallel lines never meet, and the angles of a triangle always add up to 180 degrees. In a flat universe, the expansion would continue forever, gradually slowing but never stopping, leading to a heat death where all stars burn out and all structure fades away. Second, an open universe, curved like a saddle. Here, space-time has a negative curvature. Parallel lines would diverge away from each other, and the angles of a large triangle would add up to less than 180 degrees. This geometry would drive an even more dramatic and eternal expansion, a runaway acceleration that would tear the cosmos apart. Third, a closed universe, curved like the surface of a sphere. In this scenario, space-time loops back on itself. Parallel lines would eventually meet, and the angles of a triangle would exceed 180 degrees. This finite, spherical universe would contain enough matter and energy to eventually halt the expansion through its own gravity, causing everything to reverse course and collapse back into a singularity, a cataclysm often called the Big Crunch. Which of these fates is our own depends on a single cosmic number, the average density of all the matter and energy in the universe. There is a critical density, a precise threshold that would result in a perfectly flat universe. If the actual density is higher than this critical value, gravity wins and the universe is closed. If the density is lower, expansion wins and the universe is open. For decades, astronomers have been weighing the cosmos, adding up all the visible stars, the dark matter, and the mysterious dark energy. The results from powerful missions like the Planck Space Observatory have delivered a staggering verdict. The universe appears to be flat, or so incredibly close to flat that we cannot measure any deviation. This means the cosmic density is almost exactly at the critical value, suggesting an expansion that will continue to slow for all eternity, never quite ceasing but growing ever more feeble. This geometric finding points towards a cold and lonely end, a universe that simply fades away over trillions of years. Yet this apparent flatness is itself a profound mystery. Why is the density so perfectly balanced on this razor's edge? The most compelling explanation is a theory called cosmic inflation, a moment of unimaginably rapid expansion in the first fraction of a second after the Big Bang. This inflationary burst could have stretched the fabric of space-time so violently that any initial curvature was smoothed out, leaving behind the flat, vast universe we observe today. Our fate, it seems, was sealed in the first fleeting instance of creation, locked in by the primordial geometry of the space-time fabric. While our everyday lives feel locked into a single timeline, the universe has already provided us with a verified blueprint for traveling to the future. The phenomenon of time dilation is not just a curious effect. It is a functional time machine sanctioned by the laws of physics. The most famous illustration of this is the twin paradox. Imagine one twin boards a starship and embarks on a journey at a significant fraction of the speed of light, perhaps 90%, to a distant star and back. The other twin remains safely on Earth. For the traveling twin, the voyage might feel like just a few years, but upon returning to Earth, they would step out to a world where decades or even centuries had passed. Their Earth-bound sibling would be elderly or long gone. This is not a trick of perception. Time itself, for the moving twin, genuinely slowed down relative to the stationary frame of reference on Earth. Their heartbeat, their thoughts, their aging process, all operated at a reduced rate compared to the rest of the universe. This paradox is resolved by the fact that the traveling twin experienced acceleration to turn around and come home, breaking the symmetry between the two. The clock that underwent the journey simply experienced less time. A more dramatic and perhaps more feasible method would be to orbit a black hole. The immense gravitational field creates such extreme time dilation that a single orbit for a brave astronaut might last just an hour for them, while outside the gravitational well, 50 years could elapse on Earth. They would return to a society half a century more advanced. The catch, of course, is the staggering energy required. To accelerate a spacecraft to even a fraction of light speed demands more energy than our entire civilization currently produces. And getting close enough to a black hole to use its time-warping power without being spaghettified is a formidable engineering nightmare. Yet, the principle remains unshakable. The universe does not forbid travel to the future. It merely posts a very high price for the ticket. This is not science fiction, but a direct consequence of the flexible fabric of space-time. A thrilling possibility written into the very equations that govern our reality. Traveling to the future is a proven possibility. But what if the three-dimensional world you are moving through is itself an illusion? One of the most radical ideas in theoretical physics dares to suggest exactly that. The holographic principle proposes that all the information needed to describe our universe, every star, every person, every atom, might be encoded on a distant, two-dimensional surface that surrounds us. Our rich, three-dimensional reality, with its depth and volume, could be a vast and incredibly complex projection, a cosmic hologram. Think of a credit card hologram, a flat sticker that creates a shimmering, three-dimensional image. The principle suggests our entire cosmos might operate on a similar, though far more sophisticated basis. This staggering concept did not emerge from pure philosophy, but from the paradoxical physics of black holes. When matter falls into a black hole, it seems to vanish, taking its information with it. This posed a deep problem for quantum mechanics, which insists information can never be truly destroyed. The brilliant physicist Stephen Hawking calculated that black holes slowly evaporate by emitting radiation, eventually disappearing entirely. This created the infamous black hole information paradox, where the information about what fell in appears to be lost forever. To resolve this, scientists explored the idea that all the information about the stuff that fell into the black hole is not lost inside the singularity, but is somehow smeared and stored on the black hole's event horizon, its two-dimensional boundary. The entire three-dimensional interior of the black hole could, in theory, be described by the information painted onto its two-dimensional surface. The holographic principle takes this black hole logic and applies it to the entire universe. If a volume of space can be described by information on its boundary, then perhaps our entire observable universe is just a projection from a shell at its outermost edge. This is more than a quirky analogy. It is a potential framework for solving the greatest problem in modern physics, uniting Einstein's theory of gravity with quantum mechanics. In this view, gravity and the very fabric of space-time are not fundamental. They are emergent phenomena, side effects that arise from the complex interactions of quantum information on that lower dimensional surface. We are living inside the projection, like characters in a simulation, experiencing a solid world that is ultimately built from a shadow play of data. While this remains highly speculative and far from proven, it forces a profound shift in perspective. The solidity of the world around you, the very space you occupy, might be a magnificent illusion, a deep and layered reality emerging from a simpler, flatter truth. This perfectly flat universe we observe poses a monumental question. How did the cosmos achieve such an exquisitely balanced geometry? The answer lies in a breathtakingly violent event from the universe's first moments, a period known as cosmic inflation. In the tiniest fraction of a second after the Big Bang, from around 10 to the power of negative 36 seconds to 10 to the power of negative 32 seconds, the universe did not just expand, it exploded in scale. During this fleeting instant, space itself stretched faster than the speed of light, doubling in size at least 80 times over. This was not matter moving through space faster than light, which is forbidden, but the very fabric of space-time expanding, a distinction that allowed this incredible growth. Think of it like this. Take a small, wrinkled handkerchief. If you stretch it slowly, the wrinkles remain. But if you could stretch it suddenly and violently to the size of a football field, every tiny crease and fold would be smoothed into near perfection. Cosmic inflation did exactly that to the infant universe. It took every region of the primordial cosmos, no matter how lumpy or uneven, and stretched them into the vast, uniform expanse we see today. This explains the first great piece of evidence for inflation, the stunning uniformity of the cosmic microwave background radiation. No matter which direction we look, this remnant heat from the Big Bang has almost exactly the same temperature, to within 1 part in 100,000. Without inflation, there would have been no time for these distant regions to exchange heat and equalize. They were simply never in contact. Inflation solved this by stating they were once part of a tiny, connected patch that was then blown up to cosmic size. Furthermore, this rapid stretching did not just smooth the universe. It also amplified tiny quantum fluctuations, the jitters from the vacuum of space itself. These microscopic ripples were inflated to astronomical proportions, becoming the seeds for all future structure. The slightly denser regions in this cosmic blueprint, imprinted on space-time, eventually collapsed under their own gravity to form the vast cosmic web of galaxies, clusters, and voids we observe today. The distribution of galaxies across the sky is not random. It is a direct fossil record of those quantum seeds stretched to an immense scale. This theory of inflation, while still theoretical, provides the most compelling explanation for why our universe is so large, so flat, and so uniform. It was a pivotal chapter in the life of space-time, a sudden, explosive growth spurt that set the stage for everything that was to come. That restless quantum sea of virtual particles is not just a theoretical fantasy. We can actually feel its push and pull. The Casimir effect provides a stunningly direct proof that the vacuum of space is alive with fleeting energy. Picture two perfectly smooth, uncharged metal plates placed incredibly close together in an absolute vacuum, separated by a gap narrower than 1,000th of the width of a human hair. In the emptiness outside the plates, the quantum vacuum can spawn virtual particles of all possible wavelengths, from the incredibly long to the vanishingly short. But in the narrow gap between the plates, only certain wavelengths can fit. It is like the difference between an open ocean, where waves of all sizes can roll freely, and a narrow canal, which can only support waves of specific sizes that match its width. The quantum fluctuations between the plates are restricted, while the fluctuations on the outside are not. This creates a difference in the radiation pressure. The frantic activity of virtual particles on the outside of the plates exerts a stronger push than the more limited activity happening between them, with more pressure pushing inward from the outside than exists pushing outward from the inside. The two plates are forced together by an invisible, inexorable force. This is not gravity or magnetism, it is the literal pressure of nothingness itself. This bizarre attraction was first predicted by the Dutch physicist Hendrik Casimir in 1948, and it has been confirmed by numerous precise laboratory experiments since. The Casimir effect is a beautiful and tangible bridge, connecting the abstract mathematics of quantum field theory to a phenomenon you can, in principle, reach out and measure. It shows us that what we call empty space is not a passive stage but a dynamic participant, a seething ocean of potential from which everything, including the very atoms in our bodies, ultimately emerged. The void itself has a structure and a force, woven intrinsically into the fabric of space-time. But if the vacuum itself is a sea of energy, what does that tell us about the very structure of the stage? At the absolute smallest scales, the smooth, continuous fabric of space-time dissolves into a state of pure chaos. This is the hypothetical world of space-time foam, a turbulent, frothing reality at the Planck length, a distance so minuscule it is almost beyond description. Here, the gentle curves of general relativity are replaced by a violent, probabilistic frenzy. Quantum fluctuations are not just happening in space, they are happening to space itself. The geometry of the universe is constantly bubbling, warping, and twisting. In this frenetic sea, tiny wormholes may spontaneously blink into existence, connecting two random points for an immeasurably short moment before pinching off and vanishing. Microscopic bubbles of space-time may form and dissolve like foam on an ocean wave. This is not empty space, but a seething, boiling caustron where the very concepts of here and there lose their stable meaning. This foamy nature represents a fundamental limit to our knowledge of the cosmos. There is a point beyond which we cannot measure a distance or an interval of time with perfect precision, because the ruler you are trying to use and the clock you are trying to read are both jittering uncontrollably, built from the same unstable quantum foam. The stage itself has a fundamental resolution, a pixelated graininess that prevents us from seeing a perfectly smooth reality. This wild idea is a crucial piece in the puzzle of uniting gravity with quantum mechanics. It suggests that on this unimaginably tiny scale, space and time are not the smooth backdrop of Einstein's universe, but a dynamic, ever-changing substance, constantly being rewritten by the laws of quantum probability. We cannot yet test for space-time foam directly, as its effects are far too small for any instrument we can conceive. But its theoretical existence paints a breathtaking picture of the true nature of reality. A universe built not on a calm, solid foundation, but on a restless, quantum sea of infinite potential. That chaotic quantum foam hints at a reality far more fragmented than we ever suspected. Our own universe, with its four familiar dimensions and specific physical laws, might be just one isolated bubble in an infinite cosmic froth. This is the staggering concept of the multiverse. The idea emerges naturally from the theory of eternal inflation, a variation on the cosmic inflation that shaped our early cosmos. Picture the primordial universe as an endlessly boiling pot of water. Our entire observable universe is just a single bubble that formed when inflation's rapid expansion stopped in one localized region, allowing for stars and galaxies to form. But in this vast, eternally inflating background, other bubbles are constantly nucleating at random, each one a self-contained universe with its own distinct properties. The moment inflation ends and a bubble locks in its local laws of physics. In this grand cosmic lottery, the fundamental constants, the strength of gravity, the mass of an electron, could be different in every single one. We live in a bubble where the numbers allow for complex chemistry and therefore life, a selection effect known as the anthropic principle. We could not exist in the vast majority of other bubbles, where the physics might be too hostile for any structure to form at all. Some of these bubble universes could have more than 3 spatial dimensions, or a different arrow of time, or no matter at all. The philosophical implications are profound. It suggests that every possible version of reality might actually exist somewhere in this greater multiverse. The question of whether we could ever observe these other universes is a daunting one. Since each bubble is embedded within an eternally inflating space that is expanding faster than light, their boundaries are forever receding from us, hidden behind unreachable cosmic horizons. We are like sailors on a ship in an infinite ocean, unable to see the other vessels because the fog between us is expanding too quickly. Some theories suggest that if two bubbles were to collide, it might leave an imprint on the cosmic microwave background, a circular bruise on the sky. Scientists have searched for such patterns, but so far, none have been confirmed. The multiverse concept stretches our understanding of space-time to the breaking point, forcing us to confront a cosmos of literally infinite possibilities, a reality so vast that our own existence feels both incredibly special and infinitesimally small. Even a black hole must obey certain cosmic rules. The Bekenstein-Hawking area theorem declares that the total surface area of a black hole's event horizon can never shrink. It can only remain constant or grow larger over time. Think of the event horizon as the black hole's skin, its point of no return. This law means that black holes are fundamentally voracious entities. Whenever they consume matter, energy, or even other black holes, their surface area must increase. This simple, powerful statement about geometry has a startling parallel in the world of thermodynamics, the science of heat and energy. The second law of thermodynamics states that entropy, the measure of disorder in a system, always increases. A shattered cup has higher entropy than a whole one, and the universe relentlessly moves toward greater messiness. The fact that a black hole's area behaves exactly like entropy suggests a profound and hidden connection. It implies that the surface area of a black hole might literally be a measure of its entropy, a way to quantify the incredible disorder hidden within its dark heart. This was a theoretical masterpiece for decades, a beautiful piece of mathematics waiting for a real-world test. That test came with the dawn of gravitational wave astronomy. When the LIGO Observatory detected the ripples from two black holes colliding, it provided the perfect laboratory. Scientists analyzed the signal and calculated the event horizon areas of the two original black holes. They then calculated the area of the new, single black hole born from their violent merger. The result was a resounding confirmation. The area of the final black hole was indeed greater than the sum of the two initial areas, just as the theorem demanded. This was not just a victory for theoretical physics. It provides a crucial clue in the greatest quest in modern science, the search for a theory of quantum gravity. The link between a black hole's area and its entropy hints that the fabric of space-time itself may be woven from microscopic, quantum units of information, painted onto the boundary of a black hole like pixels on a screen. Every time a black hole grows, it is not just gaining mass. It is adding to its cosmic ledger of disorder, obeying a fundamental law that binds the very large to the very small. This universal present you feel right now is a powerful illusion. According to the laws of physics, your now is not the same as everyone else's. Special relativity shatters the idea of a single, universal moment flowing from the future into the past. The reality is that simultaneity is relative, entirely dependent on your state of motion. Imagine a flash of light occurring at the exact center of a speeding train car. For a passenger sitting inside that car, the light reaches the front and back walls at the same instant. Those two events are simultaneous in that frame of reference. But for an observer standing on the platform as the train races past, the story is completely different. From their perspective, the back of the train is moving toward the point where the flash happened, while the front is moving away from it. Therefore, the light will strike the back wall first, and only later reach the front wall. The very same two events, which were simultaneous for the passenger on the train, are now clearly separated in time for the observer on the ground. Neither perspective is wrong. Both are equally valid, and this is the unsettling truth about our universe. There is no privileged clock ticking at the heart of reality, no cosmic director calling out now for everyone at once. This profound relativism of simultaneity forces a radical rethinking of time itself. It supports the idea of a block universe, a static four-dimensional structure where the past, present, and future all exist with equal reality. In this view, your birth, your reading of this sentence, and every moment of your future are all just fixed points in the vast, unchanging geometry of space-time. The flow of time, the palpable sense of a present moment slipping into history, becomes a kind of cognitive artifact, a story our brains tell us as we move along our individual world lines through this eternal block. What you perceive as the vivid, immediate present is merely a local projection, a slice of the greater cosmos that is unique to your path through it. This is not just an abstract theory. It is a fundamental property of reality that challenges the very core of our conscious experience, leaving us to wonder if the feeling of now is the deepest truth we know, or the most convincing trick our minds have ever played. Our understanding of causality, the very rule that cause must precede effect, rests entirely on the cosmic speed limit of light. But what if that limit could be broken? The equations of physics do not explicitly forbid particles from traveling faster than light. They merely state that nothing with real mass can be accelerated to that speed. This loophole opens the door to one of the most mind-bending hypotheticals in all of science, the tachyon. A tachyon is a purely theoretical particle that is born moving faster than light and can never slow down to the speed of light or below. To exist in this state, such a particle would possess what physicists call imaginary mass. This does not mean the mass is make-believe. It is a mathematical term indicating that its squared mass would be a negative number, a concept that has no direct physical analogy in our everyday world. The bizarre consequences do not stop there. According to some interpretations of the math, a tachyon would experience time in reverse relative to us. From our perspective, its effect could be observed before its cause, shattering the logical sequence of the universe. Imagine a tachyon carrying a message. You could theoretically receive the message before it was ever sent, creating an unresolvable paradox. If you then decided not to send the message because you had already received it, how could the message ever exist in the first place? This is the kind of causality violation that makes physicists deeply skeptical of tachyons' existence. They are not part of the established standard model of particle physics, and despite numerous searches, there is not a single shred of experimental evidence that they are real. For now, they remain a fascinating ghost in the mathematics, a tool for probing the absolute limits and logical foundations of our theories. They challenge us to ask how deeply the concepts of cause and effect are woven into the fabric of space-time, or if they are merely emergent properties of our particular corner of a much stranger cosmos. This staggering mismatch between prediction and reality is known as the cosmological constant problem, and it represents the most embarrassing failure in modern physics. Our two most powerful theories of reality, quantum mechanics and general relativity, are telling us two completely different stories about the energy of empty space, and they disagree by a number so vast it defies human comprehension. On one hand, quantum field theory describes the vacuum as a seething foam of virtual particles. Every cubic centimeter of empty space, according to this math, should be bursting with a colossal vacuum energy. The calculations suggest a value so immense that it should be curving the fabric of space-time into a tight, microscopic knot. Yet, when we look out at the cosmos, we measure the actual energy density of the vacuum from the universe's accelerating expansion. This observed value is not just a little bit smaller than the quantum prediction. It is one followed by 120 zeros times smaller. This is not a minor rounding error. It is the equivalent of predicting a tsunami that would drown the entire planet, and then observing a single, gentle ripple in a teacup. This vacuum energy, or the cosmological constant, should be warping space-time so violently that stars and galaxies could never have formed, and the universe would have ripped itself apart in its first instant. The fact that we exist at all, gazing out at a vast and structured cosmos, means that something is profoundly wrong with our understanding. Either our quantum calculations for the vacuum are missing a crucial piece of physics, or our theory of gravity is incomplete on the largest scales, or both. The cosmological constant problem is the screaming paradox at the heart of our quest for a final theory. A stark reminder that the deepest nature of space-time still holds its greatest secrets tightly locked away. That same cosmic warping that creates black holes also sculpts the light from the distant universe. Gravitational lensing transforms enormous galaxies and galaxy clusters into nature's own telescopes, bending the fabric of space-time so dramatically that it distorts our very view of the cosmos. When light from a faraway galaxy travels toward us and passes near a massive foreground object, it does not travel in a straight line. Instead, it follows the curvature of the warped space-time around that object, its path bending just as a marble would roll along a curved surface. The result is a cosmic mirage. The background galaxy can appear stretched into long, luminous arcs, like streaks of paint across the sky. In a perfect alignment, where the background object is directly behind the foreground mass, the light can be bent into a complete circle, a shimmering halo known as an Einstein ring. These are not mere artistic interpretations. The Hubble Space Telescope has captured countless such images, revealing ghostly blue arcs and perfect golden rings that are the unmistakable signature of space-time itself being bent by unseen mass. But this phenomenon is far more than a celestial curiosity. It is one of astronomy's most powerful tools. Just as a glass lens in a telescope can magnify a distant object, a gravitational lens can amplify the light of galaxies so faint they would otherwise be invisible. This allows us to peer deeper into the universe than ever before, studying the formation of the very first galaxies born not long after the Big Bang. Crucially, gravitational lensing provides our most direct method for mapping the invisible architecture of the cosmos, dark matter. We can see how the light from background galaxies is distorted, and by meticulously mapping that distortion, we can calculate the total mass of the foreground cluster causing the lensing. The shocking result is always the same. The amount of visible matter, the stars and glowing gas, is nowhere near enough to account for the immense warping we observe. The majority of the mass is completely dark, revealing its presence only by the way it bends the light traveling through its gravitational field. Every arc and every ring is therefore a dual discovery, a glimpse of an incredibly distant object, and a precise measurement of the invisible dark matter scaffold that holds the cosmos together, proving once again that the flexible fabric of space-time is not just a stage, but an integral part of the performance. Despite their terrifying complexity, a black hole's true nature is remarkably simple. The no-hair theorem tells us that an isolated black hole can be described completely by just three numbers: its mass, its electric charge, and its spin. Everything else, every single detail about the star that collapsed to form it, the planets it swallowed, or the astronauts who tragically fell in, is entirely erased from the universe's view. All that intricate information is lost behind the veil of the event horizon, leaving behind a cosmic object of stunning simplicity. Imagine taking a library filled with millions of unique books, each with its own story, characters, and knowledge, and compressing it into a single, featureless stone. The stone has weight and perhaps a slight magnetic charge, and it might be spinning, but all the stories are gone forever. A black hole is that stone. This radical simplification poses one of the most fundamental problems in modern physics: the black hole information paradox. Quantum mechanics, the rulebook for the universe, states that information can never be truly destroyed. It can be scrambled, but it must, in principle, be recoverable. Yet, according to the no-hair theorem and Hawking's own work on evaporation, black holes seem to be the ultimate shredders, permanently deleting information from reality. This is not just a philosophical debate. It strikes at the heart of whether our universe is predictable and governed by reliable laws. If information can vanish into a black hole and never return, then the entire framework of quantum physics, and by extension our understanding of cause and effect would need to be rewritten. The solution may lie in the holographic principle, suggesting the information is not lost but encoded on the event horizon's surface, a faint, two-dimensional imprint of everything that fell in. For now, the paradox stands, a profound reminder that the universe's most chaotic and destructive objects might also be its most elegantly simple. An accelerating observer does not experience the same empty void as everyone else. Hurtling through what seems like a perfect vacuum, they would find themselves bathed in a faint, warm glow of radiation. This is the Unruh effect, a strange prediction from the marriage of quantum theory and special relativity. For an observer moving at a constant velocity, the vacuum is cold and empty, a true void. But if that same observer begins to accelerate, their detector will click with the signature of real particles. It is as if the very act of acceleration excites the quantum fields, causing virtual particles to condense into a detectable heat bath. The faster the acceleration, the warmer this phantom glow becomes. This bizarre phenomenon is a direct cousin to the Hawking radiation emitted by black holes. In Hawking's case, it is the intense gravitational field at the event horizon that plays the role of the accelerator, tearing virtual pairs apart. In the Unruh effect, it is raw motion itself that conjures particles from the seeming nothingness. This reveals a profound truth that shatters our classical intuition. A particle is not an absolute object. Whether you detect a particle or just empty space depends entirely on your own journey through the cosmos, on your state of motion through the flexible fabric of space-time. An astronaut floating freely would report a cold, empty void. That same astronaut, firing their engines to accelerate, would report a warm sea of particles in the exact same region of space. Both are correct. There is no single, God's-eye view of what is truly there. This intimate link between acceleration and particle creation points to an even deeper unity, hinted at by Einstein's principle of equivalence. The physics you experience in an accelerating rocket ship is indistinguishable from the physics you feel standing in a gravitational field. The Unruh effect extends this beautiful connection into the quantum realm, showing that acceleration can mimic gravity so perfectly that it even heats up the vacuum. Our reality is not a fixed backdrop. It is a personal experience, a story written by the interaction between our own motion and the restless, quantum heart of space-time itself. Perhaps the universe has a built-in security system to prevent temporal chaos. Stephen Hawking, deeply troubled by the paradoxes of backward time travel, proposed his famous chronology protection conjecture. He argued that while Einstein's equations of general relativity might mathematically allow for closed time-like curves, paths that loop back on themselves in time, the laws of physics will always conspire to prevent them from actually forming. Hawking suspected that the weirdness of the quantum world would always come to the rescue of causality. Imagine trying to construct a working time machine. As the machine powered up, creating a region where time could curve into a loop, the vacuum of empty space would react violently. According to quantum theory, a flood of virtual particles with infinite energy would spontaneously appear and focus on the nascent time loop, creating a feedback effect that would destroy the machine before it could ever be activated. It would be like a cosmic circuit breaker, instantly tripping to prevent a short circuit in reality itself. This elegant idea offers a compelling answer to a classic question. If time travel to the past is possible, even in principle, then where are all the time tourists? The chronology protection conjecture suggests they are not here because the universe simply does not allow it. The laws of physics seem to have a profound vested interest in protecting the integrity of history, ensuring that the past remains immutable and paradoxes like killing your own grandfather remain firmly in the realm of fiction. Our comfortable sense of a flowing present moment may be the most profound illusion of all. This brings us to the 30th astonishing fact, a puzzle that links the quantum heart of reality to our everyday experience of time. At the subatomic level, particles do not exist in single, definite states. Instead, they exist in a blur of all possible states at once, a condition known as quantum superposition. An electron is not simply here or there, it is smeared across a probability cloud, with odds of being found in any number of locations. This strange condition is described by the wave function, a mathematical entity that encapsulates all these possibilities. The profound mystery, known as the measurement problem, arises when we try to observe this system. The moment we measure or observe the particle, this blur of possibilities seems to instantly snap into a single, definite reality. The wave function is said to collapse, choosing one concrete outcome from the infinite menu of maybes. This act of observation appears to introduce a fundamental now, a privileged moment where possibility crystallizes into fact. It feels as though our conscious awareness is what forces the universe to make up its mind, creating a flowing sequence of nows that we perceive as time. But what if that is not what is happening at all? One compelling interpretation, the many worlds theory, offers a radically different picture. It suggests that the wave function never actually collapses. Instead, at the moment of measurement, every single possible outcome does indeed happen, but each one plays out in a newly branched parallel universe. In one reality, you are watching this video. In another, just a split second different, you decided to click on something else. There is no single moment of collapse, no special now. The entire multiverse simply exists, a static, four-dimensional block where every possible history and future is equally real. In this timeless view, the flow of time is an emergent illusion, a story our consciousness tells itself as it travels along one specific path in an infinite, branching tree. The quantum weirdness of the very small and our classical experience of a flowing time are not separate problems. They are two sides of the same cosmic mystery, forcing us to ask whether the river of time is a fundamental current of the universe, or merely a reflection of our own journey through its endless possibilities. These 30 glimpses into the cosmos reveal a universe far stranger and more wondrous than our ancestors ever dared to dream. Space and time are not a rigid, impersonal stage. They form a dynamic, flexible fabric, a living entity that bends, ripples, and even shudders under the influence of matter and energy. We have seen how gravity is not a force but a curvature in this fabric, how time itself is a personal experience that slows near massive objects or at high speeds, and how black holes represent its ultimate tearing. We have explored the quantum frenzy of the vacuum, the potential graininess of reality, and the haunting possibility that our entire universe is a holographic projection. Each of these facts systematically dismantles our everyday intuition, replacing it with a grander, more mysterious truth. The cosmic stage is an active participant in the drama, not a silent backdrop. This journey does not end here. It is part of a continuing human quest, a story of curiosity that stretches from the first stargazers to the engineers of gravitational wave observatories and the scientists preparing the next generation of space telescopes. As Carl Sagan so beautifully reminded us, we are a way for the cosmos to know itself. That exploration continues with every question we ask. We want to know which of these facts reshaped your view of reality the most. Share your most mind-blowing moment in the comments below. And if you enjoyed this journey through the fabric of the universe, be sure to like this video and subscribe for more cosmic mysteries. Keep looking up, and never lose your sense of wonder.